All right, so welcome to the first lecture of week 6 of Introduction to Philosophy Online, Philosophy 1500.01, or 2 rather. Have I been saying 0.01 the entire time? I don't know. Anyway, it's 0.02, not that it really matters. So what we're going to be doing this week is continuing with truth tables, right? But our primary focus is going to be complete truth tables, right? All of the rows, right? And we're going to focus on classifying statements. So there are a bunch of interesting logical properties that individual statements have, and that pairs or sets of statements have, and we're going to use truth tables to figure out what those are, right, and be able to recognize them. So sort of what we've been doing, right, is going through, we're studying validity. This is sort of a way station on the way to studying validity, but it's important, right? It's going to give us more facility with truth tables, right? And it's also going to start to build us up to complete truth tables for arguments, right? So this stuff's important. It might not seem obvious how it relates to validity, but wait until next week and we'll see how it does. Right, so what I want to start with is just a quick review of our logical connectives and their truth tables, right? So here's the truth table for the tilde, right? So if P is true, then tilde P is false, right? And if P is false, tilde P is true, right? So the tilde flips the truth value we've said, right, from true to false and from false to true, right? So at this point, you should know this. Right, so next we have the truth table for the dot or for and, right? So 4 possible combinations of what the conjuncts could be, right? So P is a conjunct and Q is a conjunct. So they could both be true, in which case P and Q is true. P could be true and Q false, right? In which case P and Q or P dot Q is false. P could be false and Q could be true, right? In which case P and Q or P dot Q would be false, right? That's our third row in the truth table. And then finally, they could both be false, in which case P dot Q or P and Q is false, right? So remember, conjunctions require that both conjuncts be true, right? So a conjunction is true if and only if both of its conjuncts are true and it's false otherwise, right? So if one's true and the other's false, or if they're both false, the whole thing is false. All right, so next we have the truth table for the wedge or. Right, so again, 4 possible combinations of what the disjuncts could be, right? So P could be true and Q could be true, in which case P or Q is true. P could be true and Q could be false, in which case P or Q is true, right? P could be false and Q could be true, rather, in which case P or Q is true, right? And if they're both false, right, then P or Q is false, right? So the rule here, right, is that a disjunction is true if and only if at least one of its disjuncts is true. Right, so if they're both true, or the first one is true, or the second one is true, then it's true, right? And if they're both false, it's false. All right, continuing our review, we have the truth table for the horseshoe, the if-then, right? So again, 4 possible combinations of truth values for the antecedent and the consequent. Remember, in this case, the antecedent is what, well, in every case, the antecedent is, right, the bit that goes before the horseshoe. Right, and the consequent is what goes after, right? So here we have our our antecedent true and our consequent true, right? That would be P is true and Q is true, in which case, if P, then Q is true, right? In the case where our antecedent is true and our consequent is false, right? If P, then Q is false, right? In the case where our antecedent is false and our consequent is true, if P, then Q is true, right? And if they're both false, if P, then Q is true, right? So again, there's a rule to remember here, right? Which is that a conditional statement, if P, then Q, or of that form, right, is true if and only if it's not the case, right, that its antecedent is true and its consequent is false, right? So the only case where if P, then Q is false is if the antecedent is true and the consequent is false. All right, and then finally we have the truth table for the triple bar, right? The if and only if, right? So again, four possible combinations. if both the left and the right-hand side are true, it's true. If the left-hand side is true and the right-hand side is false, it's false. If the left-hand side is false and the right-hand side is true, it's false. And if they're both false, it's true, right? So a statement of the form P if and only if Q is true, just in case both its left-hand side and its right-hand side have the same truth value. Otherwise, it's false, right? So when they're both true, it's true. When they're both false, it's true. And when one is true and the other's false, it's false. All right, so what we're going to be doing today is complete truth tables, right? So in a sense, we've already done this, right? If you remember back to last week, there were a few that we went all the way through, right? And not only that, right, by doing the truth tables for the logical connectives, we've done complete truth tables. So at this point, we're not adding really anything new. We're just sort of making explicit what it was that we were doing the entire time, right? So we want to complete a truth table, or complete a complete truth table, rather, for this statement. It's not the case that if P, then Q, right? So again, we go through and we set up our truth table, true, true, false, false, true, false, true, false, right? Two T's under P, and then followed by two F's, and then Q, TF, TF, right? And again, this makes sure that we have all of the possible combinations of truth values, right? The reason that these truth tables work, right, is that they give us all of the possible combinations. So if you only had 3 rows in this truth table, right, there's something you don't know. And that's bad because, well, in this case and in many other cases, what you don't know is what's going to hurt you. Okay, so anyway, we've set up our truth table, right, and last week we focused on how to solve these things, right? There's a certain order we have to follow. I'm going to assume that you've internalized that order. Right, so what I would suggest is pausing the video right now, right, and writing this out, and then trying to solve it. Right, so here are a few hints. Right, so we're going to start with our individual sentence letters, and then we'll work from the inside to the outside of the parentheses. Okay, so pause me and see what you come up with. All right, so the first thing you should have done, right, is fill in underneath the individual sentence letters. So in our first row, P is true and Q is true. In our second row, P is true and Q is false. In our third row, P is false and Q is true. And then in our fourth row, they're both false. Right, so the next thing you want to do is solve for the horseshoe, right? We want to work from the inside out. Right, so this is the next thing to solve. And of course, the thing that you would use here is just the truth table for the conditional, or the horseshoe. Okay, so when P is true and Q is true, it's true. When P is true and Q is false, it's false. Whenever the antecedent is false, it's true. Oh, actually, we have a mistake here. Note the fourth line of the truth table. I meant to do this. Actually, no, I didn't. It's just a mistake. Note the fourth line of the truth table. That F underneath the conditional should be true. Right, so this is going to mess us up, but it's a learning moment. Nobody's perfect. All right, so next we want to solve for the not. Okay, so again, this is going to flip the truth value. I'm expecting there's going to be a problem in the fourth row, but let's go. Actually, no, there isn't. I compensated for the error. Okay, so anyway, you should have false, true, false, false, right? And it's flipping the truth value, right? So what we've done, right, is completed an entire truth table for an argument, right? So what we were doing last week is that I'd specify something like, suppose P is true and Q is true. What is the truth value of, it's not the case that if P, then Q, right? And then we would solve for, say, just the first line. Right, but I could have kept giving you the same one and specifying each row in the truth table, in which case, once you like shoved them all together, right, you would have a complete truth table. So that, in effect, is what we're doing. Okay, so think back to the truth table for not, or the tilde. It only has 2 rows. Everything else that we have done has 4 rows. So why is that? So think about it for a moment. Pause me and think about it. Okay, so the reason, right, has something to do with this. We want to make sure that we have accounted for all of the possible combinations. So think about the tilde, right? It attaches in the truth table to a single statement. Now, there's only one way that, there are only two ways that statement could be, right? It could be true or false, right? So those are all the possible combinations. So that's why we only have two rows there. Now, think about a statement that has two, or a proposition that has two statements, two simple statements. How many possible combinations are there? Well, there's the one where they're both true. There's the one where one's true and the other's false, and the other one where the other one is false and the other one's true, right? And then finally the one where they're both false, right? So there are four possible combinations. Okay, so here's a mathematical formula so you can figure out how many rows, right? Remember, rows go across. There are in a truth table. So the number of lines in the truth table is 2 to the nth power, where n is the number of different simple statements in the proposition. Okay, so what does that mean? Well, let's think about this example. So how many different simple statements are there in this proposition? Well, there's P and there's Q. Are there any others? No. Okay, so there are only two. So 2 to the second is what? Well, this isn't very difficult mathematics, right? So you should know this. 4, right? So there are 4 lines in the truth table for it. It's not the case that P and it's not the case that Q. Okay, so how about this one? How many different simple statements are there? Well, it turns out there's only one, right? P. So 2 to the 1th is, or first, is 2, right? So there are going to be 2 lines in the truth table for it's not the case that P and P, right? So remember, when we're counting, or the thing to keep in mind here, right, is that when we're counting different simple statements in the proposition, we're counting simple statement types rather than tokens. So here's a way to think about the difference. How many letters is in the word Boston? Okay, so you might answer 6, right, or you could answer 5. So 6 would be to count each individual letter as it occurs once. So B, O, S, there's 3, T, O, N, there's 6, right? But if we count sentence or letter types, right, then we're not going to count O twice, right? So there'd be B, O, S, T. Oh, we've already counted O, N, 5. So count by types, not tokens. So think about the statement or the proposition that we have here. It's not the case that both not P and P. Okay, so there are 2 occurrences of P, right? So there are 2 tokens of P, right? But there's only one type, P, right? So the answer here is going to be 1. So we only do 2 rows rather. You could do 4 rows, but it would be redundant. Right, so how about this one? We'll figure it out on your own. Right, so you should come up with 4. What about here? Again, pause me if you need to and come up with it. So 2 to the 3rd is 8, right? So there are going to be 8 lines in this truth table. So we've never seen one that big before. But we'll see what that looks like here in a moment. But don't let it intimidate you. It's just the same as what we have been doing, only a little bit bigger. All right, so here we are. We're going to do it. Okay, so let's set the truth table up for this, right? So our proposition, if P, then if Q, then R, right, has 3 different simple statements, P, Q, and R, right? So we know it's going to have 2 to the 3rd rows. 2 to the 3rd is 8, right? So there'll be 8 rows. So again, what we want to do with this P, Q, and R business is make sure that all of the possible combinations are represented. So that's easy when we only have 2 letters, right? There are only 4. And we can sort of keep track of it just by looking. But it gets much more difficult when we get into 8. Right, so here's how you would set this up. You'll have true, 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 false, 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 false under your first letter. Right. Think back to how you do it with the 2 statement ones, right? You have 2 T's and 2 F's. right? So the number of t's that you start with is half of the number of the rows. So similarly here we have 4, that's half of 8. In our next column, right, we'll have true, true, false, false, true, true, false, false. And then in our final column, we'll have true, false, true, false, true, false, true, false. Okay, so I can guarantee you that if you always do it this way for these three simple statement ones, you're going to have all of the possibilities. If you don't do this way and you just try to do it on your own, you might get it right, you'll probably get it wrong. It's too much to keep track of. Okay, so now we've set up the truth table. Let's solve this. Okay, so this might look intimidating because it's bigger, right? But it's still just the same idea, right? We're going to go through and we're going to put our sentence letters underneath, we're going to put our truth values underneath the sentence letters, and then we're going to solve from the inside out. Okay? Right, so it's something you've already done. So pause me right now, set this up, right, and solve it. All right, so here's what you should have come up with. First, we'd start by doing this. We'd put our letters underneath, right? Okay. And again, what we've done, right, is just taken the information from the left-hand side of the table and put it into the right-hand side of the table. So very easy. Okay, so what's the next thing we do? So think about it. Okay, so we're going to solve for a horseshoe, right? We're going to solve for the horseshoe between Q and R, right? We're going to work from the inside out. So when they're both true, it's true. It's false, right, because the antecedent is true and the consequence false, and that's the only time, right, where an if-then is false. Then we have true, 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 false, true, true. Okay, good. So what do we do next? Well, we solve for the final horseshoe. So true, false, true, 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 true. Okay, good. So this is how it should look, right? And again, this is really just the same thing we have been doing, right? It's just a little bit bigger. It's fine. Right, so here's your answer, right? This is the relevant part of the truth table to look at, right? When all of them are true, the whole thing is true, right? And when P is true, Q is true, and R is false, it's false, right? But otherwise it's true, right? So the only situation in which this whole thing is false, right, is when P is true, Q is true, and R is false. Okay, cool. Okay, so here's what we've done so far, right? We've learned how to determine how many rows a truth table has, right? 2 to the n, where n is the number of different simple statements. And we've also learned how to construct a truth table for a proposition with 3 simple statements, right? It's going to have 8 rows, and then there's the business about what goes on the left side, right? So in your first row, you'll have true, 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 false, 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 false. In your second column, right, you're going to have true, true, false, false, true, true, false, false. That's 8. Good. And then finally, in your final column, you'll just alternate true, false, true, false, true, false, true, false, true, false. Okay. And if you do that, right, you're going to be guaranteed that every possible combination for those 3 sentence letters, right, statement letters, are represented. And that's what we need. Okay. So we're now going to introduce some, what I'm going to just call big ideas. Right, so first, some propositions are true in all possible situations. Okay, can you think of some? Well, here's maybe one. So it's either raining or it's not raining. Right, no matter how the world is, it's either raining or it's not raining. Right, or for any number you care to consider, either it's even or it's odd. Right, the world had to be such that that number was either even or odd. Okay, here's our second big idea. Some propositions are false in all possible situations, right? That's something like they're necessarily false, right? So perhaps 2 plus 2 couldn't have equaled 5, right? Every way the world could be, that's false. Or another example. It couldn't both be raining and not raining in the same place at the same time. Right? Or you couldn't be both alive and dead, or something like that. Anyway, those sorts of propositions, they're false in all possible situations. Here's our next big idea. Some propositions are true in some possible situations and false in others. Okay, so look, perhaps you went to school today, right? You didn't have to go to school, right? You could have failed to go to school, right? So in some situations it's true, in some it's false, right? It didn't have to be that way. Okay, so we have special names for these. So the propositions that are true in all possible worlds, we'll say that they're tautologous, right? Or that they're tautologies, right? So tautologous is the adjective, and tautology, right, is the noun form. For these propositions that are false in all possible situations, we'll say that they're self-contradictory, or that they're self-contradictories. And then finally, the propositions that are true in some possible situations and false in others, we'll say that they're contingent. All right, so let's start with tautologies. Right, so some propositions are true in all possible situations. Here's an example. So if P, then if Q, then P. Okay, so what we're going to do in the rest of the lecture is see how we can use truth tables to determine whether or not a given proposition is a tautology, or is self-contradictory, or is contingent. All right, so we're going to set up a truth table. So in a side, right, how many rows should this have? Well, only 4, right, because 2 to the second is 4, right, and there are 2 sentence letters, right, P and Q. Okay, so pause this, solve. All right, so here's how you should have started out, right? Put your sentence letters underneath, put your truth values underneath your sentence letters. Then we're going to work from the inside out. So we'll start with this horseshoe. And then we'll have true, true, false, true. All right, and now we'll end with this horseshoe. And it's true, 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 true. Okay, so let's think about what this tells us. So we have 4 possible situations, right, that represent the different ways that P and Q could be, right? The situation in which they're both true, the situation in which P is true and Q is false, the situation in which P is false and Q is true, and the situation in which P is false and Q is false, right? Those are the 4 rows. Again, each one represents a different possible situation. Okay, so note that in each possible situation, if P, then if Q, then P, right, is true. Right, so this is a proposition that's true in all possible situations. Right, so it's a tautology, or it's tautologous. Right, so what we want to be looking for, right, when we're determining whether or not a proposition is a tautology, right, is looking under its main operator, right, remember the operator that you do last, that you solve for last, in this case this horseshoe that's highlighted, and seeing whether in each row it's true. If it's true in each row, right, then the proposition is true in all possible situations, and it's a tautology. Okay, so some propositions are false in all possible situations. These are self-contradictory statements, or self-contradictories. So here's an example. P and not P. Okay, so set up your truth table, right? It should look like this to begin with, after you filled in underneath the sentence letters. Okay, so what do we solve for next? The dot or the not? Well, we solve for the not, right? Flips the truth value from true to false and false to true, right? And now we're going to solve for the dot. So it's false, right? Because T and F is false, and F and T is false. Right, so what does this show? Well, note, in each possible situation, there are two of them for how P could be, right? It could be true or false. It's false, right? So this is a proposition that's false in every possible situation, right? So it's self-contradictory, right? It cannot be the case that both P and not P. Here's another one. Okay, so let's think back to the truth table that we did, right? This is contingent. Well, let's see why. So some propositions are true in some situations and false in others, right? We're going to call those contingents, right? So what we're looking for here is whether or not the proposition is true in every situation or false in every situation, or whether it's sort of a mix, or well, not sort of, but exactly a mix, right? So if it were true in every situation, it would be what? That's right, a tautology. And if it were false in every situation, it would be self-contradictory. But if it's true in some and false in others, then it's contingent, right? So let's think back to how we solved this. So the last thing we did, right, was fill in underneath this horseshoe, the highlighted letters. Okay, so note that in many situations it's true, but there's one situation, right, where it's false. Right, so this proposition, if Q then R, right, is true in some situations and it's false in others, right? So it's contingent. Right, so here I've highlighted where it's false. Okay, so here's what we did. Right, so we've learned how to determine how many rows a truth table has using this formula, 2 to the n, where n is what? The number of different simple statement types. Second, we've learned how to construct a truth table for a proposition with 3 simple statements. And then we talked about 3 kinds of propositions and how to recognize them based on their truth table. First, there are the tautologies, right? They're true in every possible situation, right? So look at the last thing you solve for in the truth table, and if it's true on every row, right, then it's true in every possible situation, so it's a tautology. Second, we have the self-contradictories. These are false in every possible situation. So what we do is we build the truth table, look at the last row we filled, or column we filled in, right, and go down, right, and see if it's false in every row, right, then it's self-contradictory. It's false in every possible situation. And then finally, we have the contingents, right? These are true in some situations and false in others, right? So what we do is we build our truth table, look at the last column we solved for, right, the last operator. Okay, and we ask ourselves, is it true in some situations? Is it false in others? If the answer to both questions is yes, right, then it's contingent, right? It doesn't have to be true. It depends on how things are.